Hi everyone, here's our math problem for today. Let's say we wish to make a soup can in the shape of a right circular cylinder closed on both ends that will hold 200 cubic centimeters of soup. The aluminum to make the can cost 0.20 cents per square centimeter. What is the cheapest can that we can make given this situation? You can pause the video and see if you can solve this math problem. Now let's solve this problem together by first breaking up this can into its surface areas. So this top circular part of the can would now be this circle, and we have another one at the bottom. And if you are going to cut the body of the can lengthwise vertically like this and open up that body of the can, we'll be forming this rectangle. If we let the radius of the can to be r, where r is positive, then the area of these two circles would be given by a sub 1 equals pi r squared and a sub 2 equals pi r squared. Now let's say the height of the can is h, and therefore the height of our rectangle here is also h, and the width of the rectangle would be the circumference of the circle, which is given by the formula 2 pi r. And from here we know that the area of this rectangle would be the product of the length times the width, so it's 2 pi r times h for the area of the rectangle. So these are now the areas of the materials that we need in order to create this can. And according to the problem, each square centimeter of the aluminum material that is to be used for creating the can costs 0.20 cents. And our goal in this problem is to find what is the cheapest possible can that we can make. In other words, this is a minimization problem, and calculus is good at solving problems like this. So let's focus first on the total surface area, and that is equal to 2 pi r squared plus 2 pi rh. And let's remember this result. We're going to use this later on. Next, we know that the formula to find the volume of this right circular cylinder is equal to the area of the base times the height, and the base is circular and its area is pi r squared, and the height is the variable h. It is given that the volume must be 200 cubic centimeters. So let's replace this V with 200 cubic centimeters. And let's solve this for H. H is equal to 200 over pi r squared. Now let's substitute this value for H to this formula of the surface area. So what we now have is surface area is equal to 2 pi r times the quantity r plus this H is replaced by 200 over r squared. Here we just factor out the common factor 2 pi r to arrive at the second line here. This is the total surface area of the aluminum that is needed in order to create this can. And the cost of that aluminum is 0.20 cents per square centimeter. So let's multiply now the surface area by 0.20 to get our cost function in terms of the variable r, or the radius. So in here, we would like to find what is the radius of this can that can give us the cheapest possible can. Let's simplify this first by multiplying 0.20 times 2 pi r to arrive at this equation. And let's distribute 0.40 pi r to this binomial to arrive at this simplified form. This is now our cost function, and let's remember that this r cannot be 0. That r, in fact, must be greater than 0 because we are measuring radius. Radius cannot be negative. Let's investigate this cost function. The graph looks like this. There are two parts. We have this part at the left side of this y-axis, and there is another part at the first quadrant. Now, since r is greater than 0, we are only interested in this part at the right side of the y-axis. And so, let's focus our investigation at this curve. We want to find the minimum value. Therefore, we are after this lowest point here. At this lowest point of the graph, we know that the slope of the line that is tangent to this point must be 0 because the line must be horizontal. And in calculus, there is a way for us to know what is the slope of this red line, even if we do not know what is the equation of that line. Because the slope of the line tangent to the curve is the derivative of the equation of the curve. And that equation of the curve is this cost function. So if you find the first derivative of this cost function and equate that derivative to 0, then we are basically finding the value of r, which will result to a slope of 0. So let's compute for the first derivative. So let's find the derivative of the cost function with respect to the variable r, and that is equal to the derivative of the first term plus the derivative of the second term. The derivative of 0.40 pi r squared is equal to 2 times 0.40 times pi, which is 0.80 pi, and we subtract 1 from the exponent of r squared to get r. Here, pi and 0.40 are constants, r is the variable. Now, the derivative of 80 over r is equal to negative 80 over r squared, using the power rule of differentiation. Then we want to equate this derivative to 0, so let's make it equal to 0. And we want to solve now for r given this equation. So solving for r, let's multiply both sides of the equation by r squared, so we can eliminate the denominator r squared, and add 80 to both sides of the equation, and divide by 0.80 both sides of the equation to get pi r cubed equals 100, and then divide both sides by pi, and take the cube root of both sides to get r equals the cube root of 100 over pi. This is now the value of r that gives us this minimum value for the cost function. So let's remember this value for r. Now let's recall our original cost function. It's 0.40 pi r squared plus 80 over r. And let's substitute now this value for r to this cost function. Using Desmos graphing calculator, here are now the results. The cube root of 100 over pi is approximately equal to 3.17. So the value therefore of the radius that will give us the cheapest can is r equals 3.17 centimeters. Now, plugging in this value for our cost function, that gives us a minimum cost per can of 37.86 cents. And this is now the cost of the cheapest can that we can make given this situation. And therefore, this problem is now solved. So thank you very much, and we hope to see you again in our next video. Bye for now.